Membrane potential is the difference of voltage across the plasma membrane. Hello friends, welcome to Biology Concern. I am Animesh, and in this video I am going to discuss about membrane potential, how membrane potential can be generated, and what is about action potential and resting membrane potential along with their inhibitors. So let's jump into the topic. First, as you all know that ion concentration gradients across the plasma membrane. So the concentration gradient of the ion across the plasma membrane and selective movements of some ions along with the gradient creates a difference in electric potential or voltage across the plasma membrane. So what it means? It means basically if this is a cell, so there is a potential difference between outside and inside of the cell. So if we take an instrument and measure these voltage gaps between the outside of the cell and inside of the cell, we can get a particular voltage that is present across the plasma membrane. That is, inside is the negative, that consists of minus 70 millivolt, and outside is positive. So this kinds of measurement is known as membrane potential. So what is resting membrane potential? So whenever a cell is not producing any electrical signal, its membrane potential is resting phase. That means there is no difference in the membrane potential. So that is why it is known as resting membrane potential. So there is no change of voltage. So what is the action potential? So a sudden fast transitory and propagating change of the resting membrane potential is known as action potential. So whenever a particular cell is stimulates by a external stimuli, so external stimuli whenever applied to a cell particularly, this sudden fast and transitory propagation of the change of the resting membrane potential is known as action potential. That means a cell excites and it creates a voltage difference between these outside of the cell and inside of the cell and disrupt this resting membrane potential minus 70 millivolt, and that is the action potential or action membrane potential. So basically, if we considered this diagram of about membrane potential, so this is the membrane potential and this is the time. So resting membrane potential is minus 70 millivolt and there is an action potential of plus 30 millivolt. So there is a zero in here. So whenever we applied stress or stimulus here, so whenever we applied stress or stimulus here, then the cells gets excited and it allows the rapid influx of sodium ions, just like this below structure. I will elaborate later. So basically this stimuli opens sodium gated channels and membranes get depolarized. That means membrane potential comes 30 plus 30 millivolt from minus 70 millivolt. So from minus 70 millivolt to plus 30 millivolt, this change is known as action potential and it is known as depolarization of the cell. So basically it is the depolarization of the cell. So whenever a depolarization occurs, a membrane potential is generated, and by those membrane potential this cell can excite it. After the excitement of this particular cell, now the cell has to come its original state, that means resting membrane potential. So in this phase repolarization occurs, and in this repolarization K plus channels rapidly opens, that is the potassium channels. So potassium channels rapidly opens, and by the help of potassium ion the membrane going to its original state, that is the minus 70 millivolt at the stage of repolarization. But here K plus channel still opens, so the membrane potential does not halt at minus 70 millivolt, rather it reflects greater and crosses minus 100 millivolt. So cross minus 100 millivolt here, and whenever it touches the minus 100 millivolt, it again depolarize and create a polarization to fix this excess repolarization, and this excess repolarization fixing step is known as hyperpolarization. So hyperpolarization basically fixing of the excess repolarization of the membrane. That means, so So K plus channel still open and they moves out the potassium channels from inside to outside of the cell, and ultimately it settles down at the minus 70 millivolt, that is the resting membrane potential. So this is the graph basically depicts the depolarization, repolarization and hyperpolarization of the membrane. So whenever we consider this is a cell, if this we consider this is a plasma membrane and this is the gated channels here, so there's a 4 step of these gated channels. So first one is the closed. So whenever this gated channel first closed, the activation gates is closed but inactivation gates are open. So basically these dots are inactivation gates and this is the activation gate. Okay, so whenever any stimuli comes, then both gates are open. That means activation gate and inactivation gate both get opened and the maximum influx of sodium ion occurs, and this influx creates a depolarization. That means opening of the Na plus channels creates a depolarization and membrane comes from minus 70 millivolt to plus 30 millivolt. So after that occurred, these channels is now partially inactivated. That means activation gates are still open. So this is the activation gate. So these activation gates are still open but this inactivation gate is still closed. So inactivation gate is now closed. So whenever a sodium ion can enter into this particular cell, if a sodium ion wants to enter into the cell, they cannot enter because the inactivation gate is closed. Now the sodium ion reflects back to the outside of the cell and sodium cannot get inside of this cell. So that is why this is known as inactivated stage. And the final stage, there is a closed stage where activation and inactivation gates, both gates are closed. So if the membrane gets at equilibrium position, so whenever a membrane is in the equilibrium position, then electric potential occurs of the membrane equals to the K plus equilibrium. So the electric potential that is generated within the membrane and outside of the membrane, the both electric potentials or volts are in now equal condition. So in this condition we can explains it by Nernst equation. So Nernst equation shows us that Ek, that is the equilibrium condition of this voltage, is represented as RT by ZF ln Kr, concentration of Kr by concentration of Kl. That means R, where R stands for the gas constant, that is 1.987 calorie degree inverse mole inverse. T stands for absolute temperature, that is 293 Kelvin at minus 20 degrees centigrade. Z is for the charge, that is equals to 1. F considers as Faraday constant, that is 23062 calorie mole inverse V inverse. And Kr and the Kl is the concentration of K plus ion on the right side and the left side of this equilibrium state. So whenever a cell is in equilibrium condition, then the all factors are considered is here are expressed by this Nernst equation, and those equation helps us to depict this, particularly the equilibrium state of a particular cell. So, and there is some inhibitors also present of these gated channels or voltage gated channels. So one is known as glycine and second one is GABA. So glycine is the major inhibitory transmitter that is present in the spinal cord, and GABA, that is gamma aminobutyric acid, also present or more abundant in the higher brain region, that is hippocampus and neocortex. So in neocortex and hippocampus, GABA is more predominant, where GABA inhibits these stimulatory responses and by which they inhibit the action potential. And in the spinal cord, glycine is present, where glycine is inhibits this generation of the action potential, and thus it halts the stimulus or the cell's action potential. So if you like that video, please hit the like button, don't forget to subscribe, and thanks for watching.